Hello again. Let's get started. And thank you all for coming again. Welcome to the third seminar of the Priberam Machine Learning Lunch Seminars. Today we have with us João Bento from Feedzai, and he will talk about his work, Explainability for Sequential Decision Making. João Bento is currently a research data scientist at Feedzai, working on explainability for machine learning models. He obtained his master's degree in computer engineering at the Instituto Superior Técnico, and his thesis, which resulted in today's work, was advised by Professor Pedro Soleiro and Professor Mário Figueiredo, and it was a collaboration between Técnico and Feedzai. João's main research interests include deep learning explainability and transparency. So without further ado, João, you can lead the way.
So, hello everyone. I think you guys can hear me. So thank you, Ruben, for the introduction. As Ruben said, my name is João Bento Souza. The work that I'm presenting here is titled Explainability for Sequential Decision Making, and resulted. It was my master thesis that I delivered in January. And the advisors were Professor Mário Figueiredo, which I think is present, and Pedro Soleiro from Feedzai. So the work was a collaboration between the university, Técnico, and Feedzai. So without further ado, the agenda of the presentation. First, I'll give a little bit of an introduction. Then I'll present the related work gathered for this work. Then I'll present our method, TimeSHAP, followed by some case studies to validate it, and ending with the conclusion. So, due to the business setting that Feedzai works in, which is prevention of financial fraud, it's a sequential a domain which is sequential in nature. And this work focuses on fraud detection, which is a sequential decision-making task. But what is a sequential decision-making task? It means that when you are making a prediction, you need to consider the history of that of the decision subject that you're trying to predict upon. So when you are trying to predict fraud at transaction 4, you need to consider, for instance, the transactional history of the card or of the client, for instance, 3 transactions, the last 3 transactions. You can also transpose this to other domains, for instance, electronic health records, where to make a prediction of a disease, you will consider the previous doctor visits or electronic records from the patient. So the state-of-the-art model in this kind of sequential decision-making tasks are called recurrent neural networks, or their variants like long short-term memory networks or gated recurrent units. But the problem with this is that these methods are considered black boxes on their reasoning. So they have complex decision-making systems in order to make these complex predictions, and the problem is that their decisions become obscure to humans, and we can't understand why they make the decisions that they make. So there is a tension between the accuracy and the interpretability of the recurrent neural network models, because the more accurate and complex and larger the model, the harder it is to interpret their results. So understanding these decision processes is paramount for several target personas, as it is the case with data scientists who need to understand the models, to develop them, debug them, and having some accountability on their decisions, as end users, which will trust the model's predictions in order to make a decision and improve the accuracy or the time to decide. So, for instance, in the example of healthcare, the doctor will look at the prediction and make a decision about the diagnosis. But you can also add more personas, like the decision subject, which is the person that is being diagnosed, that wants to know why it was diagnosed the way it was. So there is not much research work on explainability for sequential decision-making tasks, specifically on tabular data. So the objectives for this work was to develop an explainer for sequential decision-making tasks based on tabular data, and our explainer should attribute importance on both features and events. And events here we consider like events or instances of features. So the electronic health record, a sequence has, for instance, 5 electronic health records or 5 transactions in our case, and each event or each transaction has several input features. It must be post-hoc because in our use case, we want to bring explainability to already trained models. So models that are already in production, we want to explain them. And it must be model agnostic because we want to be agnostic on the architecture, and we want to be agnostic on the framework, and we want to be agnostic on the model itself. So the model might be only available to us through a prediction-based API. So we will give input data, the transaction or the sequence of transactions, and we get just a score, like a text representing the score of the sequence. So for the related work, there are 3 main approaches on the literature to explain recurrent neural networks or sequential decision-making tasks. The first one is based on gradient explainers, the second one is attention mechanisms, and the latter is model agnostic. And looking at, we made this table here, which is kind of a literature roundup table. And what will happen is throughout the presentation, we will fill this table here. So gradient-based explanations are based on the gradients of the underlying model being explained, and they are obtained by differentiating the output with respect to the input. So we do this for each input feature, and we get a value. These methods, because they use the gradient of the model, any noise that affects the gradient will affect the explanation. So gradient saturation, gradient non-linearities, or in specific case of recurrent neural networks, the vanishing gradient detailed here in this work. So for our table, gradient-based methods are not model agnostic because they need to have access to the gradients of the model, of the prediction. They are post-hoc because we can explain already trained models. They are adapted to the sequential setting, meaning that they can explain recurrent neural networks and sequential decision-making tasks. Its computational cost is low, and on the reliability, we have that the noise that affects the gradient will affect the explanations. Looking at attention mechanisms, these mechanisms will allow models to learn how to focus on certain parts of the input, which they themselves learn to consider relevant. And the attention mechanism will calculate a weight for each input that the model is attending, and then weigh each input accordingly to form a context vector. So if we take a sequence of events, each event will be weighted according to the importance given by the model, and a context of the whole sequence will be formed, and a prediction is made on the context. The rationale here is that the attention weights are then served as the explanation for that model, because the attention weights will represent how much the model attended to that input. So looking at our table, attention mechanisms are not model agnostic and they are not post-hoc, because the explanation is built in the model. So when you are developing the model, you need to create the attention mechanism. It is adapted to the sequential setting. Its computational cost is none, because when you are making a prediction, you are already calculating the weights. So serving them has virtually no cost. And on the reliability, there is still a lack of consensus on the literature if attention weights can be considered faithful or can produce faithful explanations, as detailed in these 3 works here that try to answer this question. So looking then at the model agnostic approach, but focusing on the SHAP method, SHAP is a model agnostic explainer and approximates the local behavior of a complex model, F, with an explainable feature attribution model, G, which is usually a linear model. So the learning of our explainable feature attribution model, which is in our case is mostly linear models, is then framed as a cooperative game where the model score, which is the score of our complex model, gave to the instance, must be fairly distributed across the features. So in this case, the events and the features of the events that compose the instance itself. The solution to this learning task is given by the Shapley values, which is a solution to a game theoretical problem of distributing a reward across the players of a cooperative game. So because SHAP treats the underlying model as a black box, it uses perturbations to understand and explain the black box's decisions. So it probes the black box with different inputs and tries to extract information from those perturbations. So a perturbation H of an input vector X converts a binary mask 0, 1, which is as the number of features of our input, into the original feature space. But what does this means? So SHAP, essentially what it is trying to do is trying to understand the importance of each feature, and to do this, it will turn off features and turn on other features in order to understand the impact on the model. So for instance, the model will try only the feature A and see the model score, then only feature B and see the model score, then A with B, and all of these combinations, possible combination of features turned on and turned off together in order to extract conclusions. The problem here is that you cannot, if you train a model with 10 features, you can't give just feature A to obtain a score. You need to have inputs in the same shape as the models that the inputs that you train the model upon. So turning off a feature doesn't actually mean remove the feature from the input, but actually what it means is that we input an uninformative background value for that feature. So in our case, it's the average or the median for numerical features, and the mode for the categorical features, but what on the training data set, sorry. But essentially what we're trying to do is that turn off the feature will be an uninformative background value. So in order to make a perturbation, we have our instance X that we are trying to explain. We have our background values, so our uninformative values for each feature, and our binary mask, so our perturbation will turn off features 2 and 4. So our perturbation will look like this, where on features 2 and 4, we will input the background uninformative values. So we took him, the colors should help a little bit with the reasoning. So this behavior is modeled by this equation here. So to obtain all the exact Shapley values, SHAP needs to test all 2 to the power of m coalitions, which is intractable, is of exponential complexity. So in order to get around this, the creators of SHAP approximate the true Shapley values or the exact Shapley values by random sampling coalitions. So they take all the set of all possible coalitions to the power of m, they sample several coalitions, they test those, and they calculate the Shapley values from that set of random sampled coalitions. But this introduces a stochastic component. So you change the random seed, you will get different coalitions being tested, and therefore the explanations will look different or might look different. So SHAP is then formulated as this equation here. So our complex model given a perturbation will be our interpretable linear model given the perturbation mask, which will look like this linear model here, where the coefficient that is learned by this linear model W will be then served as a feature importance. SHAP explanation satisfied 3 properties. So local accuracy, which means that the sum of all feature attribution values will equal to the model score. Missingness, which means that if a feature does not impact the model, its attribution must be 0. And consistency, which means that if a feature contribution to the model increases, then its attributed importance should not decrease. So looking at our table again, we have that SHAP is model agnostic and post-hoc. We have that is not adapted to the sequential setting. That is not a current implementation for SHAP to the recurrent setting. its computational cost is very high because in order to obtain the values, you need to sample a lot of coalitions to obtain the explanations. So imagine that you sample 2,000 coalitions, you will have to score 2,000 sequences or 2,000 inputs with your black box. And on the reliability, we have some explanation variance. Due to the business constraints at Feedzai, we decided to focus for our attention for this work on the model-agnostic approach, but this does not invalidate the attention approach or the gradient-based approach. SHAP was what we went with. So now that we looked at the related work, let's look at TimeSHAP, which is the method that we developed on the master thesis. Sorry. So a little bit of background to understand what is explaining a sequential decision-making task. When you are trying to explain a sequence, what you are trying to explain is looking at this matrix here, where you have n events and n features. What you are looking at is at the matrix, where imagine you have the events will be transactions and the features will be, for instance, the amount of the transaction or the location of the transaction, the time of the day, naming a few examples. And when you are trying to obtain event level explanations, what you are trying to say is that which was the most relevant transaction or the most relevant visit to the doctor, you are trying to actually say what was the most relevant column of the input. And when you are looking at feature level explanations, we are analyzing rows. So which row was the most relevant to the input? And given that we are working on a matrix, we can actually say which was the most important cell. So instead of transaction 3 being the most relevant or the amount throughout the sequence, with cell level explanations, we are saying the transaction amount at transaction 4 is the most relevant cell of the input. Looking at TimeSHAP now, given that introduction, our method TimeSHAP builds on top of SHAP and leverages its properties, extending it to the recurrent models. And TimeSHAP uses the same formulation as the SHAP framework. So we have seen this formula before. The key thing here is underlined that in red is that our conclusion is that when we control the input function, the perturbation function, sorry, H, and we control the perturbation mask Z, we will control the explanations that are obtained. So what TimeSHAP does to obtain the different level of explanations is that we will introduce new types of perturbation functions. So to obtain feature-wise explanations, TimeSHAP follows the same rationale as SHAP, but now working on a two-dimensional space. So TimeSHAP will turn off features and will turn on other features, making these coalitions. But now because we are working with matrices or in two-dimensional spaces, we are turning off the feature for the whole sequence. We are turning that feature, that row off for all events. So having, for instance, this perturbation mask here, where we turn off feature 2, it means that on our input matrix X, feature 2 will be turned off for all events. And this is what we see here. Looking at this is formulated as on this equation here, and looking at the event-wise explanations, the same rationale stands where we turn off whole events. So for an event, we will turn off every feature of that event. So imagine a sequence with 4 events. We want to turn off event 2 and event 4. So in our original input, we will turn off all the features for these events, and this is what we see here. This is formalized in this equation here. But one problem that we faced when we were calculating event-wise explanations is because in our domain, sequences can be arbitrarily long. So imagine that you make 1,000 transactions on your card. Our sequences will be 1,000 events long. And this will mean that 2 to the power of 1,000 possible coalitions and even the random sampling of coalitions will not render useful explanations. So we needed a pruning strategy, something to reduce the number of events that we are considering for explanations. So what we realized is that often events are preceded by a long history of an important event. So imagine that we are trying to predict fraud in January or in this case of April of 2021. Maybe the transactions of 2019 are not relevant to predict fraud, for instance. And additionally, recurrent models rarely encode information from distant past events. So what we did is that we proposed two pruning algorithms, temporal coalition pruning algorithm and the sequence pruning algorithm, which we will analyze each one next. So the temporal coalition pruning algorithm, essentially what it does, it tries to find a group of all the events which do not matter for the decision. How do we do this? So we divide the sequence into grouped events and considered events. And in this case, the considered event starts at the most recent event of the sequence alone. And we group these events represented here in colors, the groups. And we calculate the exact Shapley values for these groups. So we will have one Shapley value, one importance for the group in green and one importance for the group in red. And how can we calculate the exact values? Because it is only two groups. We have 2 to the power of 2, which are 4 possible coalitions. So we can obtain, this means 4 perturbations. And if the importance of the group in red is lower or smaller than a tolerance given by the user, an importance, a residual importance, we prune. Otherwise, we increase the size of the considered events. And we do this iteratively until, for instance, we find that the three older events grouped together have a relatively small importance. So their importance does not matter for the decision. So what we do from now on with this algorithm is that these 3 events will work as one event together. So when we turn off to obtain explanations for this group in red, we will turn off the whole group. You can see the power of this algorithm. For instance, if you have 1,000 events on a sequence, if you prune the sequence to the last 5 elements, you reduce the complexity from 2 to the power of 1,000 to 2 to the power of 6. So the 5 most recent events plus the group in red. Now we have the other algorithm, the sequence pruning algorithm, and we approach this algorithm with a different rationale, where we use the proxy as we use the score of the model as a proxy for the importance. So we divide still the sequence in 2, but in this case we discard the events that are considered older, and we obtain the score for this event alone. And if the score of the model for this sequence here, which is just one event, is similar to the score for the whole sequence, the rationale is that the model have all the information that it needed to make that prediction. So what we do in case we don't find that sequence that can be pruned, we increase the size of the sequence with recent events until imagine that the score that the model attributes to these 4 elements is the same or is like the score that the model gave to the whole original sequence, and therefore we prune the 2 last elements of the sequence are pruned and we discard them totally. So we consider that the model needs only the information present in the events in green here. And we discard the events in red. Now that we obtained the feature level events, event level events with pruning, we go for the cell level explanations. And TimeSHAP computes these 3 levels of explanation. So feature-wise will indicate rows, event-wise will indicate columns, and cell-wise will indicate cells of the input matrix. I'm seeing a question in chat. So the sequence. I don't know if I understood the question. Maybe we can save it for later. Okay, so moving on, the cell level explanations. So, okay. To obtain the cell level explanations, individually it is intractable. So we would have to turn features cells on and off individually, and on an inputs with D features and L events, we would have 2 to the power of LD possible coalitions, which is intractable. Imagine just 10 events with 40 features, we would have 2 to the power of 40. To obtain reliable cell level explanations, we need to drastically reduce the number of considered cells. So, similar to the event-wise pruning, we develop a cell grouping strategy to reduce the number of considered cells. So the first step that we do is that we apply our temporal coalition pruning to the sequence, and imagine that we have 60 events, and we prune the sequence to the 7 most recent events. So the 53 events that are discarded by the temporal coalition pruning will be grouped together as one. So these events here in gray will be considered one cell, and we will calculate one attribution for this whole group. So we will turn off all of these cells on and off at once. Additionally, we use our event level explanations to obtain the most relevant events. So in this sequence, it was event 5 and 1, event 1 and 5. And we do the same for the feature level explanations. And our rationale here is that if the event level explanation flags event 5 and 1 as important, and the feature-wise explanation flags event 3, 6, and 9, maybe on the intersection of these columns and rows lies the most relevant features, because both the explanations on different axes flag those cells in particular. So what we did here is that these cells that are on the intersection will be treated individually. So these cells will have an attribution of their own, and we group all the cells in gray and all the cells in green. But we noticed is that this grouping strategy was too strict, and we lost a lot of granularity. So what we noticed is that instead of considering the intersection, maybe we should consider also the union. So what we do here is that after isolating the intersection cells, what we will do is that we will group the relevant cells of the event which are not on the intersection. So in this case, it's these cells here in light blue. This will be one group, and the other group will be of the other event here in darker blue. And we do the same for the feature-wise. So we do the same here. And in the end, we will have this grouping strategy. And don't get confused here. These groups vertically in dark blue are distant groups. We just put in the same color because otherwise this would have been a rainbow. But essentially we would have events in gray is one group, in green is another group. Each intersection cell is another group individual, and then the union of the events and on the features. Then we will turn off these cells together and obtain their individual importance. So the whole cell group will have one importance. Now that I explained the method, let's look at some case studies that we utilized to validate our method. We applied our method on 2 different recurrent neural network models that are GRU based. And these 2 models were applied to 2 different real-world banking data sets that are privately owned by Feedzai. I'm sorry. One of them is an account takeover data set, and the other one is a transaction fraud data set. So different use cases. For the account takeover data set, we first look at the pruning algorithm. We use the temporal coalition pruning algorithm, and we look at the importance of the elements of the calculation. So in red, we will have the importance of the most recent events. And in blue, we have the importance of the group older events. And we see as we increase the size of the recent events, the events that are pruned, their relevance drops significantly until they are pruned at event 9, if I'm not mistaken. So this sequence here has 286 events in total. So to calculate event level explanations individual, we would have 2 to the power of 286, but our method prunes the sequence to the 9 most recent events. Therefore, we reduce the complexity to 2 to the power of 10. So 9 individual events plus the 277 events that remain. Looking at the event-wise explanations, we see that some curious things. The first thing that I need to tell you is that because we are on account takeover data set, we have different types of events. We have transactions, which means an exchange of money between accounts. We have logins, which is, for instance, you logging in on your banking app, and we have enrollments, which represent some account setting behavior change. So you change your device, you change your password, you change your location, some account behavior setting. And one thing that we noticed in this case and in other cases is that the most relevant event is an enrollment, followed by a login, followed by several transactions. And this is a pattern that we saw that was common. And our belief is that it represents, for instance, an hacker logging in from a new device or changing the password, then logging into the account with the changed password and placing transactions that are not valid. This is a pattern that occurred a lot on this data set. Another interesting thing that we noticed here is that the transaction that we are looking at and scoring does not matter at all for the model. It is zero, it has a zero relevance. So what happens here is that the model, through the hidden state of the recurrent neural network, had already made up its mind that this was a fraudulent sequence. So having looked at the event level explanations, now looking at the feature explanations, we see that the most relevant features are transaction type and event types. So these are features that encode different level of granularities of the events, but having these features considered relevant means that the model noticed that the fact that the enrollment was an enrollment was important. So the account changing behavior setting, followed by the client stage. And we noticed that the owner of this sequence was on a little bit later stage. He was a little bit older. And we know that this is an indicator of some susceptibility to account takeover fraud. And then it was followed by location features of the transactions. Looking at another account, we have 47 events in total, which were pruned to 11 events. We see here the behavior of the pruning, and we group 38 events together. In this case, the most relevant event was the event being analyzed, so the transaction. And what we saw is that the most relevant events were 2 transactions separated by 3 logins, and these logins had virtually no importance. And the most relevant events were event transaction 0 and transaction -4. And when looking at the feature explanations, we see that the most relevant feature was the transaction amount. Analyzing the raw feature data for these transactions, we saw that the amount present in both transaction 0 and transaction -4 was unusually high. So very high amounts for this account, which is also a possible indicator of fraud. Looking at the pruning results, we have that the original data set, looking at a bigger picture here for the whole data set, without any pruning, we have that the average sequence length is 182.1 events per sequence, and the median is 138.5. And as we make the tolerance of the pruning larger, so we allow the events that are pruned to have a higher importance, we see that the pruning becomes more aggressive. So for instance, with an importance of 0.05, we get that the median sequence length is reduced from 138.5 to 9 events. So reducing the complexity very heavily. The sequence pruning algorithm, I have also here the data, but we are not conducting, we still haven't conducted very much experiments on this algorithm, but we see that the same behavior is seen here. As we enlarge the tolerance, the pruning becomes more aggressive. Looking at the global explanations at the event level, we see that the event that we are looking at, so the transaction that we are analyzing, is the most relevant, and with an average contribution of 0.28 to the score. On average, this transaction contributes 41% of the score. So what it means is that the model gives the score to a sequence, and on average, the transaction being analyzed only contributes 41% to the score, and with the remaining 59% of the importance coming from previous values of previous events or the hidden state. This shows that the model is relying, we believe that this shows that the model is relying on past events to make decisions, which is corroborated by our domain knowledge, and also the capability of TimeSHAP to capture it. So looking at the feature, I'm sorry here, forgot to say something, is that when looking at the mean importance for each event, we see that we have relatively significant importances to events at least 5 events previously, but we also see that, for instance, at event minus 25, we have here one sequence where the event at minus 25 was really relevant. So we see some dispersion here of importances. Looking at the feature global explanations, we obtain that the most important features are in accordance with our domain knowledge. So the event types, the client's age, the location features. Imagine that you make a purchase in Portugal in one day, and on the other day you make a purchase on the other day. No, but on the next hour you make a purchase on the United States of America. Maybe that's a really big distance to cover in an hour. And these features are indicators of possible fraud, which the model detected and were corroborated by our domain knowledge. And at the same time, the authentication features and security features of the transactions that indicate legitimacy of the transaction. So if you are authenticated, if you have two-factor authentication on, for instance, these types of features or behaviors that increase the legitimacy of the transaction, they show up as negative on average, negative Shapley values, which means that it is bringing the score down. So indicating legitimacy on the transaction. So looking at the transaction fraud results, just moving quick, the same graphs that you are familiar with. So 136 events pruned to the last 3. The transactions that we are looking at is the most relevant one. In this case, because it is transactional fraud data set, we only have transactions. And the features that we have as the most important, here the features are censored because it's privately, sensitive information that we cannot disclose, but we see this pattern this on other accounts also. And what we notice here is that the sequences are pruned to smaller sizes. And when we look at the pruning results, we see that on average, the median sequence length for each sequence is smaller. So on the account takeover data set, the median sequence length was 138 events. Here it is 66. And with even tighter tolerances than we had before, we can prune the sequences to smaller numbers. indicating that maybe transaction fraud can be detected with smaller context and with less information than the account takeover dataset, which is also corroborated by our domain knowledge, because on transaction fraud, the fraud is more punctual, while on account takeover dataset, you need to understand more of the client's patterns, for instance. So the sequence pruning algorithms, the same insights show up. So as we increase the tolerance, the pruning becomes more regressive. And looking at the global explanations, the event at t equals 0 is still the most important, with an average contribution of 0.16. But don't be fooled by this smaller number, because on average, this event contributes to 78% of the sequence's score versus the 41%, if I'm not mistaken, on the account takeover dataset. So indicating that the context is not as relevant on this use case of fraud. Looking at the feature global explanations, the same insights show up again. Domain relevant features show up as the most relevant, while authentication related features show up as negative, indicating legitimacy of the transaction. And these are the insights that I wanted to present to you. Now for some closing remarks. For the conclusion, TimeSHAP is a post-hoc model-agnostic recurrent explainer, which we obtain by adapting SHAP to the recurrent setting. It computes 3 types of explanations, so feature, event, and cell-wise. We propose 2 pruning algorithms that reduce the execution cost and increase the explanation reliability. And we validated our method empirically through real-world analysis on 2 real-world banking fraud detection datasets. For future work, there's still a lot to do. So we want to validate our method with the target personas at Feedzai. So give the method to them and have them see how useful it is, both data scientists and fraud analysts. We want to perform an in-depth analysis of the explanations that we obtained with TimeSHAP and compare it with gradient-based methods and attention-based methods. We want to explore different perturbation strategies that are based on domain knowledge. So instead of perturbating the sequence through what I showed you before, having some domain input there and knowing that maybe we don't need to perturb the logins, maybe we just want to perturb the transactions. And we would like to develop strategies to improve TimeSHAP's computational costs, which, although the pruning helps, this method is still substantially heavy. So this was what I wanted to present to you. Thank you. If you guys have any questions, I'll be happy to answer. And thank you for being present and listening to me.
Thank you, João, for your presentation. I liked it a lot. Now, as João said, we do have time for some questions. So if you want to ask any question, you can click the raise hand button on Zoom, and I will then allow you to unmute your microphone. And you can also ask questions through the chat. Yeah, we had a question, right?
Yeah, exactly.
So we were on slide 74.
I know it is about the sequence pruning, but I don't know if I understood. So
André said, so this score is the sequence pruning. So this score in the sequence pruning is just the final model output.
Yeah, exactly. So we take the original sequence that we are wanting to prune, so all the events together represented here, and we obtain, this is our ground truth. So imagine that the whole sequence has a score of 0.8. And then we diminish the sequence size and imagine that this here at a 0.3, and we say it's still too distant, the model is not making the same prediction. And then we increase this size until, for instance, with these events here, we obtain the score of 0.79. And we say, okay, it's within a tolerance, and the model with the whole information indicated 0.8, with just this reduced information gave us 0.79. It's close enough, so the information must be enough for the prediction. There's still the assumption that if the score is the same, the rationale is the same, which is up for debate. just because you have the same score doesn't mean that you took the same rational path, but this is one approach. We still haven't explored this method really in depth. We focused more on the temporal coalition pruning because we felt like it gave us more theoretical guarantees per se.
Thank you, João. We have one question. You should probably be able to unmute. Yes.
Hi.
Hello.
Hi, João. That was really interesting. Thank you so much. So I have a couple of questions, really. The first is because I'm not familiar with the literature. Does SHAP have any statistical or like pack-like guarantees on the approximate calculation of the Shapley values?
I think there are some guarantees because the method is derived from the theoretical Shapley values obtained by Lloyd Shapley, if I'm not mistaken, proposed. There is some guarantees, theoretical guarantees, and I think I would point you to the original SHAP paper. They have a lot of material, supplementary material. I'll be honest, I'm not the most familiar with it. I've tried it. There's a lot of hard math. So yeah, there are some theoretical guarantees. If you have any doubt in specific, I would point you to the paper, or if you want to ask, I might try to go figure out and answer you offline.
Yeah, my second question was kind of a follow-up, but I'll change it because I was wondering if you tried like a pruning mechanism that doesn't do that type of sequential division.
Yeah, we have that on our to-do list. It is really interesting that you propose that. We wanted to follow some, imagine having domain knowledge to understand, like, we don't need to go sequential. Maybe all the logins will be eliminated at once, and let's see if the logins turned off are enough for the pruning, for instance. Yes, we didn't experiment, but it's in our to-do list. Yes, very interesting.
Okay, thank you.
No problem.
So thank you. We have one more question. Mariana, I think you can. Yes.
Hi.
Hi.
Hi, João. Happy
Hola.
to see you here. And congratulations for your thesis.
Thank you.
So I have a very, very simple question. Just curious how long it takes to run. You said it's still a little bit heavy, and I imagine it could be.
Yeah. We are still working on that for making internal benchmarkings. The complexity that it is very dependent on the model, because SHAP will make all the perturbations at the same time. So it takes, for instance, we still are benchmarking, not optimizing the code, but for instance, 2 seconds to obtain all the perturbations and all the perturbations. So imagine that you have 2K, you sample 2000 coalitions. So SHAP will form a 2000 by sequence length by features. I don't know if you're following, and then it sends that to the black box and says, give me the score for these 2000 sequences. And what we are seeing right now is that the burden, the great overhead of the method is the scoring of those sequences. So we are being able to optimize the method heavily by having the models run on GPU. We are still making some, trying to make some engineering tricks with the hidden states and stuff like that. But yeah, I cannot answer you like a specific number, but it depends a lot on the number of coalitions that you sample, and the overhead of the model itself. I don't know if that answered the question.
Yeah, I think that you still have to see how.
Yeah, there's still a lot of work.
How short you can make it.
Yes.
I think. Okay. Thank you, João.
Thank you.
Thank you.
We have another question from André Ferreira. Hello.
So, hi, João. First of all, congratulations. It's very interesting. So I have a couple of questions here. First of all, as you were talking about the prunings, and it seems very interesting how this can reduce the time, right? But have you actually compared the explanations with the prunings versus without pruning?
Yes, we didn't look at the explanations themselves, like the explanation values, but what we tried to do is that we utilized, I think, 10 or 20 random seeds, and it generated explanations for a whole data set with those random seeds. And then we looked at the standard deviation of the explanations depending on the random seed, and we looked how the ranking of the features changed, like if the most important feature in one random seed was different from other random seed. And what we noticed is that without the pruning, and let's be honest here, the pruning might fail per se, and the sequence length still be very large, and the same problem stands. But what happens is that we didn't look at the explanations because we were not satisfied with the degree of explanation variance that you would obtain. So I don't like this explanation. Let me just change the random seed and obtain a different one. We first applied the pruning, and then we were satisfied with the standard deviation, and then we observed those explanations.
Okay. And yeah, that makes sense. And so also in terms of the pipeline of how you use this, like, so you have the events and the features and the cell-wise explanations. So you first compute like the first two, right? The feature-wide and the events level,
yes.
And then you go to the cells, right?
Exactly. We first apply the pruning, then we go to the events and features, which can be calculated in parallel. And then we get, in order to consider an event relevant, we have like a feature threshold or an importance threshold. So if an event has a 0.1 importance or greater, is considered relevant. Yeah. And then we obtain these and we make the intersections and the groupings and like that.
All right.
So yeah, to obtain the cell, you need to calculate the rest. Yes.
Okay. And yeah, just curious also if this is public somewhere, like being open source somewhere, just for me to try as well.
Yeah, we are getting some requests to our intentions might be to open the package, because SHAP is open source and this extends SHAP. But first, we have to see internally with Feedzai, without the intellectual property. I'm not the best qualified person here to answer that question. We want to advance the state of the art, and we would like to publish this, but we have to see internally if this material can be available or not. But if you want to, you might want to send me an email or leave me your email, and if we release it, I'll send you an heads up. But either way, we have my thesis, my master's thesis is, I think it's public on Technicus website, and we also published some part of this work to a workshop, Amlets, which and the papers are on archive, I think. So yeah.
Okay, thank you. Yes, sorry, carry on, Andre. No, I don't know.
I was just thanking for the answers.
Okay. We have another question on the chat. So Ricardo is asking, is it possible that in the sequence pruning, you exclude subsets that yield such high scores that they are outside of the distance defined by the ETA?
Yes, we have curious behavior that, for instance, we are looking for a 0.6 importance, for instance. And when we look at just the previous event, we have a 0.9, and then the context just works to bring the score down. So the model just with that event is like, yeah, this is fraud for sure. And as you give context, it starts to be, I don't really know, and the score is getting is lower. Yes. That is a very, very relevant and interesting question that you remember. We saw that behavior, and we were curious by it, and we want to analyze That also because the context is serving as a legitimate indicator.
Thank you. So, thank you. Yeah. Are there any other questions? I don't think so. So thank you very much again, João. Very interesting for sure. So this is it for today. Thank you all for being here. And we'll be back in 2 weeks at the same time. So goodbye and take care.
Thank you very much. Thanks for the opportunity.
Thank you, João, and thank you all. Okay.
Bye-bye.
Bye.